Hey everyone, welcome to the May 2020 Cosmic Adventure Astronomy Lecture. My name is Dr. Valerie Rapson. I am the director and astronomer at the Dudley Observatory in Albany, New York. We hope that you're all well, and we look forward to a time when we can actually get together and do these lessons in person again. But for the meantime, we'll continue to create and post these videos so that everybody can enjoy these lessons at home. Today we're going to talk about satellites and space junk. The idea for this lesson came about when a lot of people approached me asking about these new Starlink satellites that you might have heard about that SpaceX is launching to create this mega constellation of satellites. And there's also been some recent concern about how many satellites are up there and whether they pose a danger to one another or to the astronauts on the International Space Station. So that's generally what we're going to talk about today. We'll do a brief introduction to satellites, teach you a bit about what's up there, who's been launching, and then we'll talk specifically about those Starlink satellites. Some of you may remember the launch of the very first satellite, Sputnik 1, way back in 1957. This was the Soviet Union. They were winning the space race at the time, and they were the first country to put a small satellite into outer space. It was a very simple object. You can see a photograph of it on the right-hand side of the screen there. And since then, satellites have become a lot more complicated. And there are now over 9,000 satellites that have been launched and thousands that are still up orbiting around the Earth and still functional. Many different countries have launched different satellites, and I'll show you a cartoon later on that describes exactly who has launched what over the years. But when we think about satellites, a lot of common questions come up. Questions like, where exactly are the satellites? We know that many of them are orbiting the Earth, but how high above the Earth do many of the satellites sit? How do we track these satellites? Who keeps track of the satellites that are launched, and does anybody have governance over what gets launched? What do we do when a satellite no longer functions? Do we leave it up there? Do we bring it down? What exactly happens? And many of you have asked about this Starlink satellite constellation. So why is SpaceX launching these satellites, and why are many astronomers not happy about it? And finally, how can you spot satellites in the sky? These are all general questions that I get all the time in relation to satellites, and that's pretty much what we're going to cover in today's lesson. We'll begin with a basic definition of the word satellite. The generic term satellite technically refers to any object that is orbiting another object in space. When I say the term satellite, usually the first thing you think of is a man-made object orbiting the Earth, like the cartoon on the left-hand side there. And that is indeed true. The objects that are orbiting the Earth are technically satellites. But the moon, a natural object, is also a satellite of Earth. The Earth is a satellite of the sun because those objects are orbiting around another object in outer space. So today when we talk about satellites, we're going to be referring mostly to the man-made objects. But in generic terms, satellite just means one object that's orbiting another object. We're also going to focus only on geocentric satellites today. Geo refers to Earth, centric means center, so Earth-centered satellite. Basically, we're only going to talk about satellites that are orbiting planet Earth. There are many other orbits that satellites can have. Some satellites will follow the Earth around the sun in its orbit, and there are satellites orbiting other planets as well. But we're going to focus mostly on the man-made objects that are orbiting the Earth in today's lesson. Let's talk a little bit about where these satellites are in relation to Earth's surface. The cartoon on the right-hand side is showing you planet Earth in the center, and then there's some coloring just above. There's like a cyan or a light blue color, and then this yellow region here. Those are referring to different heights above the Earth's surface where we often place different types of satellites. The blue region, which is very close to Earth, is low Earth orbit. It's technically about 110 miles up to about 1,200 miles above the surface. The yellow region, which is much larger, that's medium Earth orbit, 1,200 miles all the way up to the very specific number of 22,236 miles. And we'll talk on the next slide why that number is so specific. But that's the yellow region here, the medium Earth orbit. And then anything above that 22,236 miles, that's technically high Earth orbit. So satellites are generally placed in one of those three locations: low Earth orbit, medium Earth orbit, or high Earth orbit. There's also some dashed lines in the images. The red dashed line, which is a little tricky to see, it's basically right around the Earth, very low Earth orbit here. That's representing the orbit of the ISS, the International Space Station, and that's about 254 miles above Earth's surface. That's where the astronauts are. So they're on the ISS in low Earth orbit. And at that height above the Earth, the space station orbits approximately every hour and a half, or about every 92 minutes. The green dashed line here is a specific orbit that's called the GPS orbit. That's where most of our GPS satellites are. And it's specifically designed so that it orbits once every 11 hours and 58 minutes. So basically, the spacecraft goes around the Earth twice in one day. So those are the general places that we usually put satellites. Now, this very specific height of 22,236 miles straight above the Earth, that is a special location we call a geosynchronous orbit. A satellite at that location takes the same amount of time to orbit around the Earth as the Earth does to rotate on its axis once. So the orbital period of the satellite and the rotational period of the Earth are exactly the same. If this satellite is at this orbit and also directly above Earth's equator, it's at a very special orbit we call a geostationary orbit. If you're standing on the Earth and looking straight up in the sky at a geostationary satellite, no matter what time of day or night you look, that satellite is always going to appear at the exact same spot in the sky. If you take a look at our cartoon in the bottom right, it's showing a geostationary satellite. You can see that the yellow box, the little satellite, is going around the Earth once as the Earth rotates on its axis. And there's a yellow circle projected onto the Earth showing the visible location on the Earth where somebody in that yellow circle could look up and see this satellite orbiting around the planet. But since we're talking about a geostationary orbit, when you look up in the sky, as long as you're within that yellow circle, the satellite will appear in the same location all the time. So the satellite is basically staying above the same location at every moment in time. And there are many communication satellites and weather satellites that do this, right? We want to be able to, use these satellites to communicate and to map the weather in a specific region of Earth. So it works out better if these satellites are a geostationary orbit, so the satellite doesn't have to constantly turn to transmit information from one location to the other. It's always observing the same spot on Earth. Now there is a more slightly generic orbit, the just general geosynchronous orbit. This is at the exact same height we mentioned, 22,236 miles up, but the orbit is not exactly matching Earth's equator. So here we're showing planet Earth, and now we're showing planet Earth tipped so that it's straight up and down. And a geosynchronous satellite would not be correlated exactly with Earth's equator. It might go a little bit above or a little bit below Earth's equator in its orbit. At this location, it still orbits around the Earth in the same amount of time, but it's not always directly above the exact same spot at any moment. It actually traces out a thing we call an analemma. So on the right-hand side here, if we have a geosynchronous satellite in a very inclined orbit, the satellite is shown here in pink, and the spot that it is directly above ends up tracing out this sort of figure 8 shape. We call it an analemma. So as the satellite goes around the Earth and the Earth turns beneath it, when you look up in the sky, if you were in the region of the satellite, it wouldn't be exactly in the same spot all the time. It would trace out this figure eight in the sky, and from the satellite's perspective, it traces out a figure eight shape on the ground. So these geosynchronous and geostationary orbits are very specific, and they're very useful when you want to track or position your satellites over a specific region of the Earth and have them stay there all the time. So speaking of placing and positioning satellites, how do we actually get satellites up into orbit around the Earth? Well, when the Space Shuttle program was still functional, that was one of the main ways that we would place our satellites. A space shuttle with some astronauts would launch up, usually to low Earth orbit. It would open up the back bay and it would release the satellite. There's a photograph of Space Shuttle Discovery launching a satellite called TDRS-7. That's pictured in the bottom left-hand side there. Shuttle would go up, open the bay, and release the satellite, which would then either remain at the orbit that it was released at, or it would use some boosters to kind of move up into a higher orbit around the Earth. Without the shuttle, we just generally use rockets to launch satellites today. On the right-hand side, you can see a cartoon of a small rocket where the satellite was placed in the nose cone. And what we do is we launch the rocket to whatever height we need the satellite to be at. We drop the two pieces of the nose cone and release or let go of the satellite. Now, when we release a satellite, we have to make sure two things are happening. We're releasing the satellite at the appropriate height, and we're also releasing it with the appropriate velocity or orbital speed around the Earth, so it will remain at that height. The reason that the space station and other satellites don't fall towards Earth is because they constantly have a speed, a velocity, that allows them to orbit, to go around the Earth. And at a specific height, a satellite has to have a specific orbital velocity to remain at that height. If the satellite slows down for some reason, then it's actually going to spiral down and potentially crash into Earth and burn up in the atmosphere. If the satellite speeds up, it'll actually move to a higher orbit, and speed it up too much, we could potentially lose the satellite to outer space. That doesn't happen usually, but it's a possibility if something goes wrong. So thankfully, once you're above most of Earth's atmosphere, there's not a lot of drag. There's not a lot of air resistance or friction. So once you release a satellite, and once it's moving at a certain orbital velocity, it's generally going to stay that way for a long period of time. As we mentioned previously, since 1957, quite a few satellites have been launched into space. This graphic shows the current number of functioning satellites as of November of 2018. Unfortunately, I couldn't find a more recent image than this, but it shows generally what's happening for each country. In November of 2018, the United States had the most functional satellites at 830. China was next at 280, Russia with 147, and then some multinational satellites were about the same number as Russia, and then various other countries had less and less. In total, there's about 2,000 satellites currently orbiting and functioning around the Earth. This is not the total number of launches of satellites. As we said earlier, over 9,000 satellites have been launched, but many of them have either returned to Earth or been decommissioned, and we'll talk in a few minutes what happens when a satellite is no longer functioning, what we do with it. But right now, about 2,000 satellites are functioning. And in the right-hand side here, you can see what they're used for. A majority of them are for commercial use. So this is, phone, TV, GPS, that kind of stuff. Government use and military use, civil use, so that's people just kind of launching small satellites for fun or for research, and then various other mixed uses here. So most of the satellites in orbit are either government or military issued, or they're for commercial use, our weather, our TV, our phones, things like that. With 2,000 satellites functioning around the Earth, space is actually starting to get a little bit crowded. This graphic here tries to give you an idea of how spread apart different satellites are at different locations. So the first set of satellites here, so each dot represents a satellite orbiting around the Earth. This inner circle is low Earth orbit, so that's up to about 1,200 miles above the surface. You can see that it's pretty crowded. Out here, this 35,000 kilometer, that's the geosynchronous orbit, our 22,000 miles. And many of the satellites there are placed at Earth's equator, so you can see the dots are much, much closer together. It's really getting crowded at these two specific locations. I can show you the same information in more of a 3D view, which I think the three-dimensional view really helps here. So here again, you're seeing a lot of satellites in low Earth orbit at various locations around the Earth. They're not necessarily at Earth's equator. They can be located at any position at any time. And then this kind of inner ring here, that's the geostationary orbit, right around Earth's equator. And it's, again, really starting to get jam-packed. At geosynchronous orbit, satellites on average are only separated by about 45 miles. Now, if we think about Earth, if I'm separated by you by 45 miles, we're not concerned about bumping into one another. But with everything moving in outer space, 45 miles of separation isn't necessarily all that much. And with more satellites being launched every year, that number, that average separation distance, is only going to get smaller. It's only going to get more crowded and more dangerous to have all of these satellites in outer space. So we definitely need to consider how exactly we're going to place these satellites, where they're going to go, and we need to start being cautious about the potential for them colliding with one another. So speaking of satellites colliding and material colliding in outer space, there's a lot of stuff out there orbiting around the Earth. There's 2,000 functional large satellites, but there's a lot more generic space debris. Space debris is literally any little pieces of stuff that is freely orbiting around the Earth. This could be a small natural rock. It could be a chunk of a satellite that has broken apart. It could be a fleck of paint that has fallen off of some sort of spacecraft. Literally anything down to the size of a grain of sand or smaller, up to the size of a fully functional satellite, all of that is technically considered space debris, and we have to make sure that we track it. Right now, there are over 500,000 pieces of space debris that are larger than a marble and 20,000 pieces that are larger than a softball. You might be thinking, well, that doesn't sound too bad, right? If we're worried about collisions, if a softball hits me in the arm, it's probably not going to hurt that much. But we have to remember the speeds at which these things are moving. Much of the material in outer space is traveling at speeds in excess of tens of thousands of miles per hour, right? If your child or your grandchild tosses a softball to you and it hits you in the arm, it's probably not going to hurt too much. But if a professional baseball player throws a baseball and it hits your arm, that's going to hurt a little bit. And those balls are only traveling at around 90 miles per hour. Imagine a softball flying at you at 17,000 miles per hour. That's 17 times faster than a bullet will travel out of a rifle. That's incredibly fast speeds, and that makes even the smallest bits of material incredibly dangerous. Things that are, little tiny flecks of paint, things that are even smaller than a marble, when they strike at these speeds, they can actually create holes that are up to 30 times the size of the object that actually hit in the first place. To kind of show you how this happens, the picture on the bottom here is the exterior portion of a camera that was on the Hubble Space Telescope. It's called Wide Field Planetary Camera 2, or WFPC-2. The white part here is the exterior portion that was facing outer space when it was on the Hubble Space Telescope. And all of those holes that you see, those are locations where a small bit of space debris struck the Hubble Space Telescope. You can see that this thing is literally littered with holes. And most of the material that hit Hubble was not anything nearly as big as a softball. These are all little tiny flecks of material that struck the spacecraft and created this hole. Now that we've returned this camera to Earth, scientists have actually drilled out each one of those holes and analyzed the puncture on this camera so that they can get a better sense of how much material is out there and what types of danger the astronauts and other satellites are going to experience once they're orbiting the Earth. So while this is a terrible thing and something we have to worry about, having this camera backed on Earth is allowing us to prepare for the future. So moral of the story, we definitely need to be concerned about this space debris, and we need to track it as much as possible and try and make sure that future satellites do not create any more space debris. There's already plenty of it up there. How do we track all of this material orbiting the Earth? Well, that's actually a job for the Department of Defense. The DoD has the Space Surveillance Network, which is a collection of ground-based radar and telescopes operated by the US military, and their job is literally to track everything they possibly can. All 500,000 bits of space debris that we just talked about, that is being tracked by the Space Surveillance Network. And so are all of the satellites. Regardless of what country is operating them, the DoD makes sure that they know where everything is in outer space all the time. The picture on the bottom shows you the location of various radar devices and telescopes across the world that are operated by the Space Surveillance Network. So it's not just telescopes within the United States. There are plenty of devices across the world, including other satellites that are operating to track material in space. Now, along with just purely tracking the material, one of the other jobs that the Space Surveillance Network has is alerting different nations if they think that any of this space debris, this space junk, is going to pose a threat to either an operational satellite or the International Space Station. And if need be, some evasive maneuvers can be done to stop the debris from hitting these important objects. So how do we decide if there is enough danger to perform one of these evasive maneuvers? Well, the DoD is constantly tracking all of this material, and they can put the information into computer models, which will tell them the probability of any one bit of space debris striking a functional satellite or the International Space Station. And if the probability of a collision is higher than 1 in 10,000, usually an evasive maneuver will be conducted. So the DoD sees this danger, they'll alert NASA or they'll alert the appropriate company, and if possible, a satellite will be shifted out of the way or the International Space Station will be moved a little bit to avoid this collision. And especially when we're talking about the space station, because there are astronauts, there are human lives on board, it's crucial that we have this information ahead of time, because we don't want to end up like what happened in the movie Gravity. If you haven't seen the movie Gravity, I highly suggest you go watch it. But basically in the movie, you've got Sandra Bullock and George Clooney. They are astronauts on the space station, and the space station gets hit by all of this space debris. And as you see in the screenshot there, basically the space station gets destroyed. And we don't want that to happen to our astronauts. So we can perform evasive maneuvers with the ISS, and we have in the past. We have shifted the space station a little bit in orbit to avoid a large chunk of space debris. Now, the space station often gets hit by little stuff, little flecks of paint from old spacecrafts. That is material that unfortunately we can't track, and it has struck the space station before. It's created small punctures and it's damaged some of the windows, and astronauts have had to go out and do spacewalks to prepare or to repair those things. So this is definitely a real threat and something that we have to take very seriously so that we don't put our astronauts' lives in danger. At some point, all of our current satellites are going to reach the end of their useful lifetime. Whether they break or we launch a better satellite to replace it, we need to have a game plan of what we're going to do with the original satellites. As you've seen, space is already getting pretty crowded, so we can't just leave the old satellites up there and continue to place new ones. So right now, there are two different options for what we do with a satellite that has reached the end of its life. The first one is fairly logical. We can deorbit the satellite, bring it down to Earth, and as the satellite moves and spirals down through Earth's atmosphere, it's going to create so much heat that the satellite will eventually burn up. Literally everything will burn to little bits, and the satellite will just get completely destroyed before it ever poses any danger to anybody down on the Earth's surface. That's the simplest way of getting rid of a satellite, basically destroying it. But for some satellites, that's not really the best option. It's easy to deorbit a satellite that's in low Earth orbit because it's already very close to Earth's atmosphere and Earth's surface. But the satellites that are in geosynchronous orbit, they're 22,000 miles up. They're much, much higher above the surface. And it would actually take more energy and more effort to bring them down through the Earth's atmosphere as it would to actually move them up higher and essentially just get them out of the way. So for most geosynchronous and geostationary satellites, when we're done with them, we move them up a little bit into something called a graveyard orbit. And I know that sounds fairly morbid, but that actually is the term that we use, graveyard orbit. This graveyard orbit is a little bit higher above geosynchronous, and at that location, the satellites will continue to orbit the Earth. They won't get destroyed, they will always be there, but they'll be up out of the way. We rarely put satellites that we want to have functional above this geosynchronous orbit. And satellites placed in these higher orbits are going to be stable at those locations for millions of years. So we can move them up into these higher orbits and essentially not worry about them for the foreseeable future. So those are the two basic options. Either move your satellite up and out of the way, or bring your satellite back down to Earth and make it so that it burns up on the way down. We don't actually want the satellite to crash land on the Earth. Any new satellites that are going to be launched, they have to have an end of life plan. Basically, when you launch the satellite, you have to have a game plan for what's going to happen when the satellite is done. Either you're going to deorbit it or you're going to place it into the graveyard orbit. And all of that needs to get approved before you'll be able to launch your satellite into space. Now that we've covered the basics of satellites, let's talk specifically about SpaceX's Starlink satellites. This is a project of Elon Musk, the CEO of SpaceX, and the goal here is to build 12,000 satellites that will be launched into low Earth orbit. And what they're going to do is provide high-speed internet to remote locations all across the globe. These satellites are ultimately going to form what we call a constellation. And it's not a constellation in the typical sense of what we think of as a constellation. They're basically going to form a web where they can communicate with each other and cover the entire planet and ultimately offer high-speed internet at pretty much any location on the surface of Earth. These satellites are actively being launched and they're being placed in 3 orbital shell heights. The first shell is 210 miles above the surface. next is 340 miles above the surface, and the third is 750 miles above the surface. So all within that low Earth orbit range. And the picture on the right tries to give you a visual sense of where these satellites are. So you can kind of see where they're currently located or where they plan to be located across the Earth. The other thing you might be wondering is, well, why is SpaceX doing this, right? When we think of SpaceX, we think about rockets and going to Mars. Well, Elon Musk is a businessman at heart, and he knows how to make money. Internet providers are a $1 trillion business, and he wants a piece of that pie. So the goal is to get some chunk of that money, and all of the profits will ultimately go towards building the mission to Mars and creating a civilization on the surface of Mars. So rockets and Mars are always the ultimate goal, and Elon Musk is trying to come up with more creative ways to make money to put towards his mission to Mars program. So how do these satellites work and how do they get launched? Well, the satellites themselves are fairly small. They weigh about 500 pounds each, and they have these giant solar panels that unfurl once the satellite is in outer space. The design is really clever. They're very flat, and they can actually be easily packed into the nose cone of a rocket. The cartoon in the bottom left shows you what these Starlink satellites, one individual satellite, looks like orbiting around the Earth. And the picture on the right is an actual photograph of these satellites packed into the nose cone of a Falcon 9 rocket. There's actually 60 satellites stacked up together here, and once they're released in outer space, they'll unfurl and they'll move to their corresponding locations around the planet. So they pack all of these satellites in, they launch the Falcon 9 to the appropriate height, and then the satellites are released. The very first launch of a Starlink satellite occurred in 2018, and they were nicknamed Tintin-A and Tintin-B. Two of them were brought up via rocket, and they were released a couple hundred miles above Earth's surface. You can see it here in the video. You can see the part of the rocket on the bottom, and then Tintin-A and Tintin-B are the two devices that appear to be falling off on either side. And the video just kind of repeats there so you can see how they're released. This is a bit different than the way they release Starlink satellites now, but this was their initial conceptual test run to see if these types of satellites would actually work. The launch and deployment of the satellites was successful. They were able to communicate with them. And after that, they decided to make one specific improvement. Instead of putting these satellites at a higher orbit, maybe 1,000 miles above the surface or so, they decided to shift them down a little bit to the numbers that you saw previously. So 2, 3, and 700 miles above the surface. This would allow for easier communication and faster internet speeds, essentially. The lower your satellite is, the less time it's going to take to send signals back and forth, and the faster the speed you're ultimately going to get for communications. This is also important because the satellites are now in a much closer orbit to Earth, and this orbit also corresponds roughly with the location of the International Space Station. The more material we place in low Earth orbit, the greater the danger there is to the ISS as well as other large satellites that are in low Earth orbit. So people were originally not too thrilled about this. We try and keep certain orbits as uncluttered as possible, and especially the orbit of the International Space Station, right? They try to avoid putting material at that location as much as humanly possible. But these satellites were shifted down a little bit, and now their orbits will be a bit lower in that low Earth orbit range. Since the launch of Tintin-A and Tintin-B, 420 of these Starlink satellites have been released as of the end of April 2020. As we said before, they're generally launched in batches of 60. And in the little video that you see at the bottom here, you're watching one of those capsules filled with 60 satellites being released from the spacecraft once it's in orbit. So it looks like it's falling down, but it's actually entering orbit around Earth. And then what happens is that device will actually start to rotate, and the satellites will end up getting released at specific times. Then they will end up dispersing to make that web-like structure, that constellation that we talked about, that covers the entire planet. So as of the end of April 2020, 420 individual Starlink satellites have successfully been launched and are in operation. What does it look like when these satellites are launched? We don't have video of them actually being dispersed from their device, but we can actually watch them from the surface. And if you see the Starlink satellites shortly after launch, they look just like a little train of dots that moves across the sky. The bottom here is showing you a video of the train of Starlink satellites a day or two after the launch of one of those 60 sets. They are all in a straight line, and over time they will spread out and disperse, but initially they're all kind of in a straight line. And you see every once in a while some of them flashing. They don't have lights on them. They're not beaming light back down to Earth, not in this way. What you're actually seeing is the sunlight catching their solar panels just right, that the satellites look like they flare up. This happens all the time with various satellites that are in orbit around the Earth. If the light catches them just right, they'll flare up. Sometimes we call this an iridium flare. If you've ever heard that term before, that's when a satellite catches the sun and creates a nice bright flash of light for a few seconds in the sky. Now you can actually go outside and see this train, and you can spot the Starlink satellites. Let me show you how to figure out when to go outside and where to look. There's a great website you can check out called heavens-above.com, and the website is shown right here on the slide. Basically what you do when you go to the website, in the upper right-hand corner, there will be a box where you can click on location and you can enter your current location. I have it set for Albany, New York, but you can set it specifically for wherever your exact location is. And what that will do is it will make all of these links live with information about when you can see various types of satellites or telescopes in the nighttime sky. There's all sorts of different options. You could check out the ISS, the International Space Station, a whole bunch of different satellites. You can look for the Hubble Space Telescope. But the one we want to pay attention to here, the Starlink passes for all objects from a launch. That's basically what we're going to take a look at here. If you click on that link, it will bring you to a giant table of information like the one shown here. The last time I checked to put this presentation together was around April 21st, so it's showing me information for April 21st. But if you, whatever date you do this for, it will show you that current day's information or the upcoming days as well if there's nothing on that current date. But let's take a look at how we read this table. You've got the date on the left-hand side, so that's the date you should go outside. The name of the satellite, so these are just different Starlink satellites that are going to be visible. You've got the time that the orbit will start. It will be visible at that specific time. The time when the satellite will be at its highest point, and the time when it will no longer be visible at your location. The altitude, how high above the horizon you should look to see the satellite, and then in what direction you should look. That's the azimuth. We're going to look at the second one here because that one has the most information. April 21st, if I wanted to see Starlink 1288, I would go outside at 20:07, so that's 8 p.m., 8:07 and 32 seconds. I would look 10 degrees above the horizon, so just above the horizon. This is going to be a very low pass in the west-southwest direction. And this pass, I'm going to skip to the other side, is going to be visible until 8:14:54. So for 4, 5, 6, 7, so for about 7 minutes time, the satellite is slowly going to move across the sky. It's going to go from 10 degrees above the west-southwest. It'll approach 55 degrees, so a little more than halfway above the horizon, towards the north-northwest direction. and the satellite will set in the northeastern direction. So you can kind of figure out where those directions and locations are in reference to your home and kind of envision the path that the satellite will take across the sky. The other important thing to notice that I skipped over originally is the brightness column here. The brightness is given in magnitudes. This is a logarithmic scale that astronomers use to talk about how bright things are. And the important thing to know about the magnitude scale is the numbers are reversed. So a bigger number actually means a dimmer object. Your eyes are able to see anything magnitude 6 or smaller. So basically, any of these Starlink satellites are technically visible to the naked eye. You don't want and you don't need a telescope to see these things. The closer you are to magnitude 6, the harder it's going to be to see, especially if you live in a light polluted area. So this very top Starlink satellite that I skipped over is magnitude 5.8. It's going to be very, very difficult for anybody around the Albany area to see. But these satellites of magnitude 3 and 4, those are definitely something that you could look for. One change in magnitude is about 2.5 times brighter or dimmer than the magnitude of the previous object. So something of magnitude 3 or 4 is a decent amount brighter than something of magnitude 6. So all of these satellites, except for the first one, are something that you could observe theoretically in Albany, New York. You want to focus on numbers that are around 3 or 4 or even smaller than that. The smaller the number, even the negative numbers, often they'll go in the negative numbers. The smaller the number, the easier it will be to see these objects. So I encourage you to check out this website on your own. Look at when the Starlink satellites are going to be visible, and as the weather gets a little bit warmer here, see if you can step outside and spot any of these satellites. If the Starlink satellites were recently launched, you'll see many of them in a straight line, but as they start to disperse, they're no longer going to end up in the straight lines like the video you just saw. You'll just see one or maybe two of them slowly moving across the sky. So Starlink is a really cool idea, and providing internet to people across the world is a really noble and great cause. But as I said before, not everybody is thrilled about this. And professional and amateur astronomers are the people that are pretty angry with SpaceX right now. And let me explain why. Starlink satellites, once they launched and were moved to these slightly lower orbits, ended up being 100 times brighter than astronomers initially expected them to be in the sky. And with hundreds of them up now and thousands of them planned for the future, there's going to be a lot of additional bright dots in the sky that have nothing to do with distant stars or planets or galaxies. And these satellites ultimately get in the way when astronomers are trying to take pictures. So let me show you an example. Satellites are not new, right? There's already thousands of satellites up there, and satellites do currently get in the way. This is a really nice image of a whole bunch of stars in our galaxy, and you can see one odd feature in the image. Right here, there's a little white straight line. That is a satellite orbiting around the Earth. When satellites show up in these images, they look like white streaks that move across, and while they're annoying, they're not that bad, right? If you're trying to do science with this image, you just unfortunately have to ignore any information around the satellite path. But the rest of the image is good. The rest of the image can be used for scientific purposes. But with Starlink satellites, they're far brighter than most other satellites, and there's so many of them that what happens is something like this. This was an image of a galaxy cluster taken by the Lowell Observatory shortly after a Starlink satellite launch. Every single one of these bright white streaks is a Starlink satellite moving through the image. What they were trying to look at are these little fuzzy things in the background. Those are the galaxies. They were trying to take scientific images of the galaxies. And this picture here is absolutely useless now. All those white streaks, those satellites got in the way, and unfortunately the picture is no good. So astronomers are really, really unhappy about this because if these are the images we're going to end up with all the time, then we won't be able to do ground-based astronomy anymore. If we're constantly going to have satellite streaks ruining all of our images, we won't be able to do any astronomy unless we use telescopes that are above the Starlink satellite orbits. Now, along with just getting in the way, sometimes these satellites can actually cause damage to the cameras of the telescopes. Here we have another example. This is an image taken by a camera on the Blanco 4-meter telescope down in Chile. They were looking at stars or possibly distant galaxies, and you can see white streaks all through the image. Each one of these little rectangles is actually a separate camera, all stitched together so that they can take one big image of the night sky. And the Starlink satellites are streaking through all of the CCD cameras, totally ruining this image. But sometimes the Starlink satellites, as well as other satellites, can get so bright that they overwhelm the camera. The way these cameras work is they have individual pixels, and each pixel can only hold so much light. If you overwhelm or saturate the pixel, the light will spill out into surrounding pixels. And if you do this often to the camera, you can actually destroy and ruin some of the pixels on the camera. With the Starlink satellites being so bright, there is the possibility that if they keep getting in the way and they saturate these very sensitive telescopes and cameras, they could create long-term damage to these instruments. And that is something we definitely don't want to happen, right? It's bad enough to have the occasional picture ruined, but it's really bad if you're saturating the cameras and just totally destroying the instruments because these satellites are getting in the way. Along with just ruining the pictures, we're also concerned about radio interference. The pictures I've shown you so far are optical images, but there are radio astronomers that are concerned about any new frequencies being used by Starlink and having those frequencies interfere with the frequencies that our radio telescopes operate at. If we're looking at the night sky and we receive some radio wavelengths of light, some radio signals, we want to make sure that what we're receiving is information from outer space, right? Light from distant stars and galaxies that we're gathering. And the more satellites we launch and the more frequencies that we use for those satellites, the more potential interference there is for radio telescopes. Starlink is going to operate at two K-band frequencies, so Ku, which is 12 to 18 gigahertz, and Ka, which is 26.5 to 40 gigahertz. And that's not necessarily any special frequencies that astronomers like to use or anything like that. But literally any new radio interference is not good for our radio telescopes. So astronomers are very concerned about this, and I want to share a quote from the Vera Rubin Observatory Management Team. They say, assuming the full deployment of SpaceX's Starlink satellites, nearly every exposure from the Vera Rubin Observatory within 2 hours of sunset or sunrise would have a satellite streak. During summer months, when twilight time's longer, there could be a 40% impact on twilight observing time. So they're basically saying that a good chunk of their nighttime observation time is going to be ruined by the Starlink satellites. So I'm not saying that we shouldn't necessarily do this. We're just bringing up the idea that we need to be cautious. We need to try and minimize the influence that these new constellations of satellites are going to have on our current astronomy efforts on the ground. If this continues and more satellites are put up by SpaceX or any other company, we could get to the point where ground-based astronomy is no longer possible. And we would have to put telescopes above these satellite locations to be able to observe anything in the night sky. And that's just not something that we want to have to do. So how do we fix this, right? We don't want to tell people no. We don't want to stop the Starlink satellites from going up, but we do want to mitigate this issue. One of the simple solutions could be to just paint the satellites black, right? If we have a dark colored object, then they're not going to reflect or scatter nearly as much sunlight, and that might make them look less bright in the sky. Great idea, but maybe not the best from an engineering perspective. We have to remember that if we paint all these satellites black, black paint is going to cause these satellites to absorb a lot more of the sun's light. That's going to cause them to heat up. When the satellites are not in direct sunlight, they're going to cool off very quickly. So there's going to be very extreme temperature fluctuations that could damage the internal computer components of these satellites. If we just literally paint the satellites completely black, now you've added an additional layer of paint that could potentially flake off over time. Remember how bad it is for things even as small as little chips of paint to be flying around like bullets orbiting around the Earth. We don't want to unintentionally create any more space debris. And the third thing to consider here is it's harder to track black satellites. We want to find a happy medium between dark enough that they're not really bothering astronomers when they're taking pictures, but still bright enough that the Space Surveillance Network can easily track them. If some Starlink satellites no longer function in the future, we want to be able to visually see them with our telescopes and our technology so that we can track those bits of space debris if needed. So making them completely black is a possible option, maybe not the best solution. SpaceX actually did try this. They painted some of the satellites in what's called Vanta black. You can see it in the picture there, very, very dark black coating. And they launched one satellite with this coating. It reduced the brightness of the satellite by about 2 times, which is good, but not really enough to be super helpful to the astronomers. Another idea that's been tossed around that we don't have a ton of information about, trying a sun umbrella. Basically adding some sort of umbrella-like device, and we have no idea what this would look like. But basically try and block the sunlight from striking the very reflective surfaces of these satellites. And then the satellite could stay the same, but you're not reflecting any of the light back down to Earth. So as I said, not a lot of information about these possible sun umbrellas is available, but the engineers continue to dream up new ideas and ways to fix what is currently a pretty big issue. With all this discussion about satellites getting in the way and possible dangers of space debris and colliding satellites, you're probably wondering, well, who controls all of this, right? Some government entity must have control about who launches what, where it goes, and all of that. Well, you might be surprised to find out that it's not quite that simple. So there are some basic organizations that do have some control. In the United States, the FCC, the Federal Communications Commission, they have to provide approval for new satellites, but basically because they have control over the frequencies used, and they also do put some consideration towards space debris. It's not really their job to worry about things colliding in outer space, but they do make that consideration, especially when companies like SpaceX say they want to launch 12,000 of these satellites. Along with the FCC, there is, of course, the FAA, the Federal Aviation Administration. They're generally more concerned about the actual launches, right? So you need FAA approval to launch a rocket and get things up into outer space. But once you've conducted the launch, they have less control over what happens over that. They do pay a little bit of closer attention to the space debris idea because if something comes crashing down through Earth's atmosphere, then it becomes a problem of the FAA. So they control the launches, they think about space debris a little bit. And then there's also the International Telecommunication Union. They are the ones that work internationally. They allocate global radio spectrum coverage and satellite orbits. So you need approval from the ITU to utilize certain radio frequencies because you want to make sure that your satellite is not operating on the exact same frequency that Russia or China's satellite is operating on. And the ITU pays more attention to the satellite orbits. They're not going to allow you to place your satellite incredibly close to another satellite's orbit in outer space. But aside from that, there's no real entity, either nationally or internationally, that truly controls what is placed in Earth orbit. Nobody controls the properties or the actual objects that are launched. It's just you need approval to launch your items, and if you're going to be communicating with those objects at all, you need approval from certain organizations. But nobody is saying, what kind of paint do you have to use or exactly where and how long are these things going to be in space. While that all must be part of your plan, it's not really governed by one entity. Now, there's also been some talk about this new Space Force that has come about in the United States. It's possible that they might start to play a little bit of a role in this, especially when it comes to the military side of things, right? If more military satellites are launched, they're definitely going to have more control over things in orbit. But right now, it's really not part of their job to govern exactly what gets launched in orbit unless it has something to do with defending the nation. So to finish up, I thought I'd tell you about Starlink's future plans. Satellites are going to continue to be launched through 2027. By 2027, they hope to have all 12,000 satellites up and functional. And there's also been some talk about increasing the number, maybe even to 30 or 40,000 satellites. And that would allow easier access for more remote areas across the world to access the internet. Along with that, the FCC recently approved construction of 1 million ground stations. So you have to have ground stations that are basically small satellite dishes that will communicate with the satellites and basically help disperse the internet to the ground area. You can see some pictures of these little satellites. They're small. Here's one of them inside of a container, and here are some containers sitting on a flatbed truck. Elon Musk has said it looks like a 19-inch UFO on a stick that basically you just place and plug in. That's it. The goal was to make these things very easily to place in more rural areas or remote areas to be able to transmit the internet to people on the ground. So SpaceX and Starlink are continuing to launch more satellites and start to get all of this functional here on the ground. So that's pretty much it. That is the story of satellites and the Starlink satellites. Hopefully you enjoyed today's presentation and are now more knowledgeable about all of the stuff that is orbiting around planet Earth. I'll leave you here with a really cool picture of the Starlink satellites photographed from the International Space Station. So you can see a beautiful array of the northern lights, and then all of those little streaks with labels there. Those are individual Starlink satellites that the astronauts captured while they orbited the Earth themselves. If you have any questions, you can always reach out to me. Just email info@dudleyobservatory.org. Those emails will end up directly to me, and I will happily answer any questions that you have about these satellites or about outer space in general. So please stay home, stay healthy, and I look forward to seeing you again in the future.